Hey. Welcome to Maths with EJD. In this video, we're talking about the third part of the basic theorems of graph theory. And in this one, we are talking about the Dirac's and Orer's theorems relating to Hamiltonian cycles. Okay, of course, we had talked about the first one, which was the handshaking lemma, and secondly, we talked about the Euler's theorems. Euler's theorems here, relating to Eulerian paths and Eulerian circuits. Now it's about Dirac's and Orer's theorems relating to Hamiltonian cycles. So Dirac's and Orer's theorems provide conditions for the existence of Hamiltonian cycles. Because you already know a cycle is a closed loop rather. So Hamiltonian cycles in graphs, which are important in solving problems, which are important in solving problems, like the popular traveling traveling salesman problem, the traveling salesman problem, that is TSP, network design, and circuit routing or circuit routing, I don't know. All right, so those are that's how useful all this can be. So let's talk about the Dirac's theorem. Dirac's theorem. So Dirac's theorem provides a sufficient condition for the existence of a Hamiltonian cycle. Okay, talking about a Hamiltonian cycle is a cycle that visits each vertex exactly once and returns to the starting vertex. So, I mean, this is like bearing a bit of resemblance with Eulerian circuit. Okay. Now, talking about the Dirac's theorem proper, Dirac's theorem states that if a graph, if a graph with n vertices is connected and every vertex, you see that connectedness is always a precondition for whatever. So, I guess I want to change marker at this point. Don't mind me. I guess it's gonna change that for effect. Okay. So Let's go for that. Dirac's theorem states that if a graph with n vertices is connected and every vertex every vertex has a degree of at least n over 2, then the graph contains a Hamiltonian cycle. I think it's pretty simple to grasp this. Okay, so all you just need to know is how many vertices does the graph have? Take note of that. Then check every vertex and be sure that every vertex has a degree of at least n divided by 2. So if that happens, then you can see the graph contains a Hamiltonian cycle. So let's look at an example of what this can be. So we have this. Consider a graph with 5 vertices A, B, C, D, E, where each vertex has degree 3. Each vertex has degree 3. Okay. That's the graph we have. Each vertex has degree 3. Then we can say that each vertex, since each vertex has degree 3, of course, you already see n is equal to 5. N over 2 is 5 over 2, which is 2.5. So, and the theorem says that every vertex has a degree of at least n over 2. So if every vertex has degree 3, then it has met the condition for Hamiltonian, for Dirac's theorem, right? So since each vertex has degree 3, okay, and the graph, the graph is connected with 5 vertices. Dirac's theorem, Dirac's theorem guarantees that the graph contains a Hamiltonian cycle. Okay. So one possible Hamiltonian cycle would be A to B to C to D to E and back to A. So, I mean, you already know once you hear cycle or circuit, it's a closed path. So you go and return to where you started from. So if you will try to visualize what we have discussed up there, right? Imagine you have A, B, maybe C, D, E. This may not be the best way to represent it, but I mean, if you can guarantee there are 5 edges, 1, 2, 3, 4. This is not looking like it. Uh, Connected by 5 edges. Okay. I mean, it should look like a pentagon, I believe. So let's make it something like a pentagon. So you have A, B, C, D, A, B, C, D, and E. Okay. I think this should work. This, and this. Okay. Each vertex has degree 3. How possible could that have been? Okay, I mean, let me just leave that alone. But I mean, we can think that up. That's really possible. We can work around that. Well, I mean, the theorem is quite clear. Just trying to visualize it as much as possible. Okay, so let's move on to the Oris theorem, still talking about Hamiltonian cycles. So the Oris theorem. So here we see that Oris theorem is stronger. Oris theorem is stronger. Oris theorem is a stronger result. It's a stronger result that provides a sufficient condition for the existence of a Hamiltonian cycle based on the based on the degrees of non-adjacent vertices. So here we have a new concept coming into it, non-adjacent vertices. Okay. Now, the first time we came across this, oh, okay, I don't think, yeah, I think this is like the first time since we started this, actually. Okay, so now, what does Oris theorem itself state? Oris theorem, okay, this is where I get to change colors. Oris theorem states that if a graph, if a graph with n vertices is connected, connected means that you can travel you can travel to any vertex of the graph directly from every other vertex or indirectly through other vertices. From one vertex to another vertex directly or through other vertices. Yeah, something like that. So Oris theorem states that if a graph with n vertices is connected and every pair, for every pair of non adjacent vertices, every pair of non-adjacent vertices, U and V, the the sum of their degrees, the sum of their degrees is at least n, is at least n. Then the the graph contains a Hamiltonian cycle, contains a Hamiltonian cycle. Okay. All right. So let's take an example of that. So example, imagine a graph, consider a graph with six vertices A, B, C, D, E, F, and edges. So the edges now are, say, AB, AC, AD, BC, BD, BE, CD, CE, and DF. Okay. So AB, AC, AD, BC, BD, VE, CD, CE, and DF. Okay. Now, well, I think this is best visualized. Mm, let's try to visualize that. So you have A, B. What's the best way to connect this? A, B, C, D, E, F. Okay, I think we can do this. A, B, C, D, E, F. And what are the edges? We have A, B. We have A, AC. we have AD, we have BC, we have um we have BC, right? We have BD, we have BE, we have C CD. There's the CD, interesting. And there is also CE and there is DF. Okay. I guess I have an idea what this should be. So B and E should be a bit down. So we have B, C, A, B, C, D, E, let's say A, B, C, D, E, F, something like this. A, B, C, D, E, F. So that we have AB, we have AC, we have AD, we have BC, we have BD, we have BE, we have CD. Okay. This will still have to go, let's see. So we have CD, then we have CE, we have DF. So this is DF like this. Okay. Well, I mean, from all we have, right, we can say the graph is connected. Do we have DE? Let's be sure there's no DE, right? Uh, DE. We don't have DE. Okay. But I think we can still say the graph is connected somehow because we can travel from, if, for instance, if we travel from uh, F, we can go F this, and then go to A and then, right. So, I mean, we can say it's connected for sure. So this is what the graph looks like now. So what is the degree of A now? So we need to get the degrees out. Degree of A is 3. You can see 1, 2, 3 for A. Then the degree of B is also 3. Is it 3? Yeah, the degree of B is 4. The degree of C is 3 is 4 actually. The degree of C is also 4. Then the degree D is also 4. Degree D is 4. Yeah, it's 4 now. Degree D. Yeah, it's 4, surely. So we have AD, of course. We have BD that exists. We have CD. And then we have DF. Yeah. So the degree of D is 4. And then what else do we have? We have the degree of E. The degree of E is obviously 2. And the degree of F is just 1. Okay. So so every pair of non-adjacent vertices, for every pair of non-adjacent vertices, the sum of their degrees is at least 6. So first of all, we know the number of vertices. So can we say we know number of vertices is 6. A, B, C, D, E, F. So that's 6. Okay. Then the next thing is, for what are the adjacent sides? So adjacent sides are sides that don't have direct connection with themselves. So imagine, let's look at the adjacent sides now. So let's say adjacent. Okay. Uh, the pair of non-adjacent sides, that's actually what we want, right? So let's do that. Non-adjacent non-adjacent vertices. Okay. Then we also need the sum of degrees. Okay. Um, okay. So we'll have to look at their pairs. Okay. So we can have something like this. But we now have degree. Is this the way to go? Okay, I mean we need their degrees basically. That's the thing. So let's identify the non-adjacent vertices. So A is adjacent to D, C, and B, but it is not adjacent to E and F. Okay, so we have the non-adjacent sides now. We have A and E are non-adjacent. A and F are also not adjacent because they are not connected together, right? They aren't connected together. Then, which other ones do we have? When we go to B, B is adjacent to AC and ACED. So B is not adjacent to F. B is not adjacent to F, so we just have BF this way. Okay. Then we go to C. C is adjacent to is adjacent to A, B, A, B, D, E. So it's only not adjacent to F. So we have CF has no connection with F. That's what that means. Then when we go to D, D is connected with A, B, C, but it's non-adjacent to E and F. So we have DE, DF. So we have DE and we also have DF. Okay. Then we go to E. E is adjacent to BC, only B and C, but it is non-adjacent to A and F. Okay, it's not adjacent to ADF. ADF. That's for E now, ADF. So we have E, A, E, D, and EF. These are non-adjacent. Okay, and finally we go to F. F is only adjacent to D. It's not adjacent to so A, B, C, E. Okay, so we have F. Uh, okay, we already have AF, right? Okay, let's just say F. F is non-adjacent to it's only adjacent to D. So we have it's not adjacent to A, B, C, E. So we have F A, F B, F C, and F E. Okay, it's not adjacent to all this. Well, I mean, we can cross out some. So we already have AE. So if you have EA again, we can cross it out. So this can go. Then we have AF already. So if we have FA, it's the same. Then if what else do we have? We have CF. If we have FC, we can cross it out. We already have EF. So if you have FE, we can cross it out. So what else? So EF, we already have the ED. If you have DE already, so ED can go. Okay. Then what else? If we have BF already, FB can go. So which other one? EF. Okay, EF is okay. C, AE, AF, BF, C, F, DE, DF. Okay, good. So now we need to look at the degrees of each one. The degree of A is 3. The degree of A is 3. The degree of E is 2. Okay, the degree of E is 2. Then the degree of the degree of so the sum of everything is 5. So that's less than the number of vertices already. So that means there's no Hamiltonian cycle based on the idea already. So do we even have to keep trying? I don't think we have to worry anymore. We don't have to worry anymore because normally for every pair of non-adjacent vertices, the sum of their degrees is at least 6. That is not true here. So the number of vertices satisfying always condition. So we can say already that I mean the degree of A is 3 again, the degree of E is 2, the degree of A is 3, the degree of F is 1. I mean, I mean you don't even have to continue, But if you have at least 6 as sum of degrees, we can go on. Okay, well let me just do it for the sake of it, right? So the degree of A is still 3, the degree of F is 1, the degree of F is 1 because that's the only thing now. Yeah, DF is the only thing we have. The degree of B is 4. The degree of B is 4, and the degree of F is still 1. The degree of C is 4, F is 1. The degree of D is 4. E, the degree of E is 2. Okay, I mean, this meets the condition, right? So we have 4, 5, 5. So only DE meets the condition. So when we talk about DF, that's 4, 1. So that's 4, 1. That is 5. Then we have EF left. So for EF now, we have 2, 1. So the EF is 2, 1, which is just 3. Okay, so automatically we can say that this graph doesn't contain a Hamiltonian cycle, you know. So it doesn't already. So we can believe AE, AF, and the odd, yeah. I mean, so in this case now, you see, the only thing that meets this condition is this, but we want everything should have met the condition. That's what the rule says, right? The rule says that, you know, then if I mean, the Oris theorem states that if a graph with n vertices is connected, and for every pair of non-adjacent vertices, U and V, the sum of their degrees is at least that number of vertices, then the graph contains a Hamiltonian cycle. Okay. So we can see here that this doesn't seem to contain a Hamiltonian cycle. Okay. All right. I want to see if I can get another example of Oris theorem. All right, so we can see that since 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 the sum of the degrees of the non-adjacent sides of the graph uh are not all greater than or equal to, at least n, right? Greater than or equal to n equals 6, then the graph the graph doesn't contain doesn't contain a Hamiltonian cycle. The graph doesn't contain a Hamiltonian cycle. Okay. All right. So that's how that plays out. Let me try to see another example if this works. Um, Let me see another example. If it doesn't work, we just stated that it doesn't contain a Hamiltonian cycle. So let's do this again. So we have, let me just do A, B, C, D, E, F. I'll just draw it anyhow it's possible. So A is connected to B, C. Hope it's not the same thing. A is connected to B, C, D, right? B is connected to A, C, and E. Okay. Then C is connected to AB. C is connected to, okay, C is already connected to A and B. Then we have E now. Then D is connected to AEF. D is connected to A already, E now, and D is also connected to F. I guess I can actually bypass this. I can do this, okay, to make it uh cuter, something like this. We can do that. Okay, so D is connected to AEF, then E is connected to B, C, D, F. E is connected to B, C, D, and then F. Then what else? F is connected to DE already. F is already connected to B to DE. Now let's see. To just be very fast, I'll just do the degrees. So the degree of A, what's the degree of A here? It's just 3 here. The degree of B is also 3. The degree of C is 3. The degree of D is 3. The degree of E is 1, 2, 3, 4. The degree of F is 2. Okay. So if you look at what are the possible adjacent sides, that A, we can have A, I mean, A is only not connected to E. We can have AE. So these sides are not adjacent. And the sum of their degrees is AE. That's 7. Good. How many edges do we have? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, that's already a no-no. Okay? That's already a no-no. Okay. So that doesn't really work here. Okay. So we have 1, 2, 3. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It doesn't work. It doesn't work. So this is less than this is actually less than n. Oh, okay. Sorry. Sorry, sorry, sorry. I think I'm wrong. I mean, this is greater. Sorry. AE. A and E are adjacent. So AE is adjacent because they're not directly connected. So, I mean, this is greater than 6. There are 6 vertices. Sorry, I was getting confused there. So, AF. So, for AF, what do we have? A, this is 2, and this is 4. No, A is 3, and E is 4. A now is still 3. F is 2. So, F is 2. That means we have the sum of these two will be 6. So 6 is equal to 6. So we are good. So this is good. This is good. Then what about other adjacent sides? I mean, we have 6 vertices. So that's what we're working with. So this 6 now is the number of vertices. And the rule says that if you add up the number of degrees, it should be at least the number of vertices you have. Okay, so let's do that. So for B now, can we do B? So B is adjacent to is not only not adjacent to F, okay? Because it's not directly connected to F. Okay, maybe F and D. B is not directly connected to D. So we can have BD. So what is B? The degree, that is 3 plus D, that's 3, which is 6. Okay, good. That is also 6. So that passes. Then for B and F, we have 3 and 2, and then the rule breaks down. So we have 5. So this doesn't work. So we can still say, therefore, the graph does not contain a Hamiltonian cycle. It doesn't contain a Hamiltonian cycle. So if all the conditions are met, then we can talk about that. Um, so I mean, we may want to seek clarity on what non-adjacent sides are. What are non-adjacent sides? Non-adjacent vertices. Okay. So okay, non-adjacent vertices are two vertices in a graph that do not have a direct edge connection between them. In other words, there's no way directly linking the two vertices. So, I mean, my interpretation is right for non-adjacent side. So we are good to go. All right. So, maybe the other thing that we want to talk about is some practical applications. So I'll just mention them in passing. So we can. I mean, this video is pretty long already. So let me see some practical applications. So practical applications. Oh, this way now. Okay. Practical applications of Dirac's and Urich's theorems. So the first one is, of course, talk about the traveling salesman problem. The traveling salesman problem. Then two, uh, of course, one of the most famous problems in operations research is the traveling salesman problem. It involves finding the shortest possible route that visits each city exactly once and returns to the starting point. Dirac's and Orre's theorems can be used to determine whether a given graph representing cities and distances contains a Hamiltonian cycle and potentially simplify the problem of finding such a cycle. Then we also have it in network design. Network design. So in computer network design, Hamiltonian cycles are useful for designing resilient and efficient communication paths between various nodes. A Hamiltonian cycle can be used to design circuits that minimize the number of links required to connect a set of nodes, ensuring that each node is visited exactly once. Three, we can have robotics and path planning. Okay, robotics and path planning. Okay. So, in robotics, Hamiltonian cycles are used in path planning for robots, particularly in scenarios where the robot needs to visit a set of locations or vertices without tracing its steps. The objective is to minimize the total travel distance or time by ensuring the robot follows an efficient path. Then we have the fourth one. We have circuit routing. Circuit routing in VLSI design. In VLSI design. So in very large scale integration design, Hamiltonian cycles can be used to route electrical signals in microprocessors and circuit boards. The goal is to lay out all connections in the most efficient way, avoiding overlap or excessive length. Then of course we have number five, that is talking about drone delivery systems. Drone delivery systems. Of course, we know that in a place like Rwanda, you have drones delivering uh, blood in situations of emergency blood transfusion. And of course, you have drones delivering food and all that in some other locations. So in drone delivery systems, a Hamiltonian cycle could be applied to plan routes that efficiently connect delivery locations. By using a Hamiltonian cycle, the drone can visit each drop-off point exactly once, optimizing flight time and fuel consumption. So in summary, right, you see that okay. Yeah, in summary, you see the Dirac's and Ores theorems play a crucial role in solving real-world problems, like we have pointed out, with where visiting each node exactly once in an efficient cycle is essential for optimization. So, I mean, this has been a long one. If you have not subscribed to this channel, there's so much more coming your way as far as graph theory is concerned. So make sure to sign up so that you will not miss out on this. Then hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know if you want me to teach a topic or solve a problem. Then like and share so that more people can have access to this great content. Till I come your way again, keep networking. Bye.